As we continue our study of differentiability at a point, it's really important for the slopes on either side of a point to be smoothly connected. For example, if you have a slope of -1 and a slope of +1, it's not going to be differentiable at this point. The two slopes aren't smoothly connected. So this is describing that, okay, using that alternate definition of the derivative. So we're going to use this to determine whether this function's differentiable at x equals 0. We already know it isn't, but we're going to show that mathematically. So if we take the limit as x approaches 0 from the left, okay, and 0 from the left, we would be talking about this function. So we have negative x. Let's see, f of 0 is 0. So -0 if you want to put that, or you don't have to. I'll write it. Over x minus 0. So we get the limit as x approaches 0 from the left is negative x over x, or just -1. As we look at the other side, the limit as x approaches 0 from the right, that would be x minus 0 over x minus 0. In that case, all right, come on. All right, there we go. X over x, that's 1. -1 is not equal to 1, so f of x equals absolute value of x is not differentiable at x equals 0. A function that is differentiable at a point is said to be locally linear at that point, because if you keep zooming in, zooming in, zooming in, the slopes kind of blend together. Now this is something you're going to have to do with your calculator, but I want you to graph the f of x function in y1 and look at x equals -1/2. Okay, you got to get a little bit good with your calculator and zoom in and in and in, and in your whisks determine if each of these are locally linear. So just put part A yes or no, part B yes or no. You can describe it if you would like. Example 11, if you sketch a graph of each of these, and then we'll determine whether it's differentiable at the given point. If you would like to rewrite this, okay, we could rewrite it as this. So now it's in our standard transformation form. It's easy to see that it was moved. Our parent function of absolute value of x was moved to the left 3. And it has been stretched a little by a factor of 2. So at x equals 3, is it differentiable? No. Okay, the cube root of x. This has a graph like this. This one's also no. Okay, we'll discuss why in a second. The good old seagull graph here. Also no. This one. No. And this one. Let's see, that would be about right here. And, oops. The slope should be the same. Either way, no. So let's talk about why functions can't be differentiable. Here we have a corner. Okay, we have a vertical tangent line. The slopes get so steep in this middle part that they're actually vertical right at that point, x equals 0. This is called a cusp. Okay, this one is one-sided. It's kind of tricky, but you can't look on the right and the left of x equals 10 because there is no right. And this one, we have a jump or a discontinuity. So this leads us to a very important theorem. If f is differentiable at a point, then it's continuous at a point. Very important. If it's differentiable, then it's continuous. If it is not continuous, and this is the symbolism for that, then it is not differentiable. Okay, that's something that we need to keep in mind. we have example 12 here. We have a little bit of a graph. The slopes from either side of x equals 1 are both approaching 2, yet the function's still not differentiable at 1. And we're going to verify why this is false, okay, why this isn't happening, using the alternate form of differentiability. All right, now for the alternate form, remember we need f of x and we need f of 1. And we're taking the limit as x approaches something 1 from the left, okay? And then we'll do limit as x approaches 1 from the right. Now keep in mind, a big mistake that people make, f of 1 is only plugged into this function. F of 1 is 1. Okay, be sure to use that value. So we have the limit as x approaches 1 from the left side would be x squared minus 1 over x minus 1. If we factor we see that the limit as x approaches 1 from the left is 2. Now if we look on this side, we have our f of x is 2x minus 0.8. F of 1 is still 1. Please keep that in mind. So in this case, we have 2x minus 1.8. So now if we plug in 1, we don't get 0 over 0. We get 0.2 over 0, which is undefined. It's not 2. Okay, that is a mathematical way to show that the function is not differentiable at x equals 1. Okay, last example here, we have the symmetric form. It's just another version. So this is something you have to do to use your calculator, okay? Practice using derivatives. There should be a dy dx button or a d button. Hopefully you know how to find absolute value. If you don't, ask a question, okay? So either way, in this case, it says A, we found that, so it should be 1, but practice using this on your calculator. And this, keep in mind, we know that it's not differentiable there, but what does your calculator say? It depends on what software version you have. So please put this also in your WISC because I want to know what your calculators are saying.